when it comes to the more scientific approach of designing, as Leo had correctly mentioned, the material properties change with change in temperature. And there are three fundamentally important material properties which play a role as far as steel is concerned. Of course, the thermal conductivity also changes slightly, specific heat also changes slightly, but those we are assuming that these are not of our concern. I mean, of course, they play a role, and they play a role in determining how much temperature steel will achieve. But what is of our importance is important to us is, one, elastic modulus changes. That means material becomes softer. Yield stress changes. That means material becomes weaker. Okay. Ductility increases. That means the material becomes more ductile. Okay. More plastic deformations it can accommodate. What else happens? Thermal expansion. Okay. So thermal expansion with increasing temperatures is also a very important parameter that controls the behavior. So with some assumptions that let's say during the fire, the loads are not changing, the boundary conditions are not changing, or the boundary conditions are standard, some formulae or some methods have been developed which are given in the Indian code. The one that you see here is the equation for the column, right? Similar equations are given for the beams also, but since I have not discussed the beams, I'm not giving you the equations for the beams, but that doesn't matter. What basically matters is that what the Indian code says is that for increasing temperatures on the horizontal axis, it has the temperatures. On the vertical axis, it has the normalized values of the respective parameters at increasing temperatures. So at ambient temperature, let's say you had one elastic modulus and one yield stress. As the temperatures increase, the yield stress remains constant, remains at the same level, 1 or 250 or whatever type of steel you had. It remains at that level up to about 215 degrees centigrade, and above which it starts to decline in a linear fashion. And elastic modulus starts to follows this curve. As soon as the temperature starts increasing, the elastic modulus starts decreasing, and it follows this behavior. And at about 900 to 1000 degrees centigrade, both of these values become almost zero. Okay. These are pretty okay. I mean, at around 900 degrees centigrade, no matter how accurately you test it, you will see that the yield stress is almost like 5% of the original strength. So that's not too bad. Actually, there are some issues with this intermediate range. If I look at the European code, then this is what they say. For the yield stress, they say up to 400 degrees centigrade, the value remains constant, and then it starts to decrease at this point, at this rate. And if you come to 900 degrees centigrade, you will see it is around 7% or 8% of the ambient value. Okay, and the Indian code says yield stress becomes zero, which is okay. At 900 degrees centigrade, you hardly have any strength left. Plus a lot of creep effects will kick in. So, okay, so the European code makes all the values as zero at 1200 degrees centigrade. But I'm not too worried about what happens after 800. After 800, anyway, you can assume that the structure is almost gone. It is between what happens. It is basically what happens between 400 to 800. That's what is important, especially in the range of 600 degrees centigrade, where you are. What properties you are giving here. So if you look at the elastic modulus at 600 in the European code, it takes about 0.4, and yield stress, it takes about 0.56 or 0.55, something like that. The Indian code takes slightly different values, and overall also before 600 degrees centigrade also, the Indian code is slightly unconservative. And these clubbed with our design equations that are given in the Indian code, there's another parameter which is called proportionality limit. Now, the funny thing is that all these codes give you these values of proportionality limit, but they don't often use it for the equations. So this is the American code. In the American code, they have taken this. American code and European code, by the way, have the same material properties. Okay, material model is same between the European code and American code. So this proportionality limit is never used in the American code. In the European code also, I don't think it uses the proportionality limit. It only uses these two curves. But this also plays a very important role. And actually what has been done is that in the American code especially, they have completely changed the design equations. So the design equation that is applicable for ambient temperature for a column, for example. So this is the column design equation. Okay. So they have completely revised the design equation for elevated temperature cases. That is so that they can continue to use these E values and Fy values, which are given in the Euro code, but actually the equation, the column design equations, likewise the beam design equation also, these equations have been revised in such a way to incorporate the proportionality limit. Okay, So they have come up with a new equation, which is basically an empirical equation based on a lot of analysis, FEM analysis they did, and based on that they came up with this equation. Now this is a part of the American code. Okay. Likewise, the European equations are also there. These are based on experimental data. Doesn't matter. Still, these are empirical equations, not based on fundamental principles. And if we compare the values from the Indian code, what is this color? Purple color. So in this Indian code, values are in purple, and green and red or orange. That is American and European. So you can see that the American code values are most conservative, but they are the ones that are developed the last. So I would say these are most accurate probably, because they have compared the European code values as well as other international code values, not the Indian ones, and they have shown that theirs is more accurate and has been accepted. So European code values are somewhat unconservative, and these plots are developed at 600 degrees centigrade. So the American code values are somewhat unconservative for stockier columns. For slender columns, it is fine. The Indian code is unconservative across the board, across the range of this one. And this I have done. The Indian code I have taken, I think the class A. If you take class B or class C, then you will see that curve is slightly lower. So there can be two, three ways we can address it. Either we have to revise our equations in the Indian code. Okay. Of course, we are wrong. I mean, because when they developed the equations that are there in the American code, they had shown a lot of experimental data and FEM data, and that's how they had matched their results. So either we have to revise these equations, or we have to revise our curves, fire and time temperature, the elastic modulus and Fy curves. It's an unfortunate situation, because I don't know. There is no way for us to know the source of these curves, where they got these curves from. Who had done those tests, where is the paper, under what conditions they did these tests, because the conditions also matter a lot. So without that information, it is very difficult to say whether these curves are right or wrong, or appropriate or inappropriate for this application. Okay. So either we may have to modify these, or we have to come up with some kind of we can say that instead of using curve A, that is the alpha value, instead of using alpha value that is at ambient temperature. So if I was dealing with a column buckling in the major axis at ambient temperature, I would use alpha is equal to class 1, right? Whatever the corresponding alpha value is. But we may say no, at a high temperature applications, always use alpha that is belonging to class 3 or class 4, something like that. Yeah. So some modification like that we have to do, so that we are more at par with the international practices. Okay, this is an example. These things I decided to skip. Now in today's class, what we will focus on is some buildings. So basically, I'll show you 3-4 real life examples of buildings which collapsed or which did not collapse, were almost about to collapse, or the buildings that were subjected to very huge fire and did not collapse. Okay. So, and we will see different aspects, different ways in which fire affects the buildings. Yeah. So these are the case studies. So the first building that I'm starting today with is called Plasco building. It was located in Iran. It has collapsed completely. What happened to the video? So this building was located in Tehran, in Iran. It was a steel building, and in 2017 it caught fire and it burned for several hours, but then it collapsed completely. Here is a video of the collapse. You probably cannot hear the audio that is coming from this video, right? You cannot.
Yes, sir.
Yeah, that's okay. There is not much to hear for in this one anyway, but you can see the video. So there is a fire extinguisher who is trying to spray water into the building. And suddenly you can see a number of columns start to fail here, and you can see a lot of dust coming out of this building. So you can always search on YouTube. There must be more videos of each of these buildings that I'm talking about. So this is Plasco building. I'll play the video again just in case you missed how the collapse started. I often wonder, when this building was collapsing, what was this guy thinking? Like, he was in such a precarious situation. I mean, the building could have almost, like, you can see some of the columns were falling. In 2D, I cannot see really how far they are, but So it seems like he was at a very high risk at that time. You can hear some columns collapsing. Mostly it started from this side. See, some of these columns, these could have hit this crane. Okay. You can always go to YouTube and find more videos. So this was a pretty tall building. I don't remember exactly how tall it was. 17 story. That's a pretty tall building. It's all steel, and you can see this steel here. These are all steel members. These are columns, steel columns. This is a picture taken from outside, and you can see that steel is almost visible, right? So actually, the building in this building, some internal columns were protected with the bricks. Basically, they had put bricks around the columns. I don't know what level of precautions they have taken so to avoid fire from getting into getting closer to the columns through the gap between the bricks. But I suppose they must have done something. But looks from the videos what it looks like. They have done some investigation, but I don't think the investigation is pretty conclusive. Um, from the videos, what you can see is that some of the outer columns started to fail first, because you can see this dust coming out from one side, right? So the building caught fire on the 9th floor at 7:50 a.m. But by the time you can see the videos, the fire had spread to other floors. This was 17-story building, and I think the lower floors were already burnt out, or they were already exhausted, and the fire was at a much higher level by the time this building collapsed. So it burned for 4 hours, and 20 firefighters were trying to extinguish this fire, douse the fire. They lost life. Okay, and when they removed the debris after several days of the collapse, they found that the members, steel members, had deformed so badly they had almost molten. Right. So that means the temperatures must have exceeded 1,000 degrees centigrade. Otherwise, members would not lose their shape. For them to deform so badly that you cannot even recognize whether this is a eye flange section or it's some other member. It's all like squished together. So that kind of a thing means that the temperatures must have been really, really high at some locations. Structural temperatures. That means the building temperatures must have been even higher. The compartment temperatures must have been even higher. So this was a residential building with light commercial use, but this is how it was designed to be, primarily a residential building. So they are saying that here in this picture, you can see that breakout took place on the 10th floor or 9th floor at this location. And then the columns started collapsing, first and second collapse on the 11th and 13th floor. And the third collapse took place again on the 11th and 13th floor. So not necessarily on the floor where the fire started. The fire keeps moving up in a building, and then the actual collapse may take place somewhere else. And I don't know what this arrow is trying to make. Maybe there was some role played by these beams and internal columns also. So basically what they say is that this building was not designed for fire protection. So they might have put some bricks around this, some of the columns, but no fire protection was applied on the structural members. And this was a classic example of a building collapsing under pure fire loads. There was no other effect. There was no heavy wind. There was no earthquake. There was no damage because of any other impact or accident. It was purely fire collapse. Okay. If you look at the structural system they had used 4 heavy columns at the center, and then they had used very lightweight columns on the periphery and closely spaced. So somewhat similar structure was used in World Trade Center buildings also, the ones that had collapsed, Tower 1 and Tower 2. There also the structure was somewhat similar. You had kind of a very closely spaced light columns at the perimeter. Okay. These are tied together with heavier beams. So what investigators tell us is that this building, even though it was meant as primarily a residential building with some commercial use, it had turned out, after a period of time, people had started changing the usage of these houses. So initially, when the property was at a very prime location, a very prime property, people were not using it for this kind of a commercial activities. These are more of a showrooms and shops, etc. But later on, it turned into a go down and a workshop kind of a place. So in certain floors, certain higher floors, it was used more of a storage space, and that could have caused such a heavy fire, such a huge fire. Okay. But so as the occupancy, so in any developed city, you would see if I want to change the occupancy type of a building or usage type of a building from residential to commercial to let's say storage kind of a facility. Every time I want to do that, I have to take approvals from the local authorities, right? And in better managed cities, usually that they do a thorough job and they make sure that all the provisions corresponding to the respective usage change are actually done properly. So they are complied with. But in such cities, so Tehran also, even though it's much better developed than many Indian cities, still you can see that there was probably some level of laxity. So when they changed the usage, they either did not go for a renewed approval or a change of usage approval, or the approval was granted without a thorough check. Okay, so this can be expensive. Uh, this was the Plasco building. That was basically a basket case. So if you don't design the structures properly, even as per the existing prescriptive guidelines, you are going to have some issues, right? Now all the subsequent examples I'm going to show are from developed countries where all these buildings were mostly. There are some cases where they were not appropriately designed, but most of these buildings were appropriately designed as per the fire provisions, whatever prescriptive nature they have. But still, there were some collapses, some failures. Uh, so, and in the next couple of buildings, you will see a common theme, and that is the thing that I want to talk about. We have talked about the effect of thermal expansions in the very first couple of lectures. And under fire, how does that play a role? So let's say you have a bar which is restrained from both ends, and then I start heating this bar. Okay, so we had discussed this thing at around 100 degrees centigrade, depending on what you consider as the epsilon y value. So if epsilon y is taken as point, yield strain is taken as 0.002, then at about 190 degrees centigrade temperature, the entire bar will yield. But if you consider a beam in a building, it's not a uniform cross-section beam. The beam has some connection, some joints, some splicing, something somewhere, right? Or at least at the ends, it will have some connections. So in that kind of a scenario, even much sooner than 190 degrees centigrade, you can expect that there will be some yielding going on in the connections, because the beam would be expanding and the connections cannot expand by or cannot apply the same level of force to the beam, because the connections are not designed to have the same cross-section area as the beam. So they are weaker in compression. So connections will be compressed and they will be either deforming or bending or buckling, or some kind of a yielding will happen in the connections. Okay, so they turn into a weak link. Typically, it does not happen at 190 degrees. It happens much later. The reason for that is that the vertical restraints that are given to us are not usually 100% rigid. They are flexible, so they accommodate some level of push. Okay, and beyond a point, they start resisting, and then the beam starts to deform or starts to fail. So there may be some yielding going on. There may be some kind of a local buckling happening at the ends or in the connections. You can see some kind of something going on. Okay, at around 300 to 400 degrees centigrade structural temperature. Okay. Now, subsequently, what happens is that once that deformation has set in, let's say some yielding happened or something happened, and the beam has shrunk to accommodate this temperature rise. Okay, so beam's natural length has shrunk, but actual length is exactly same what space is available. Okay, now after the fire has died out, the beam starts to contract because that thermal expansion coefficient is still applicable. So now the entire beam is contracting, and you have held the beam strongly at the two ends. Now two things have to happen: either these connections will fail because your natural length of the beam had shrunk to this level now, and now it is shrinking back. Some of this will be elastically deformed, but again, some portion of it has to be accommodated. And then if the connections are not able to deform accordingly, then the connections are going to have this issue of rupture. So connections rupture, that is one issue during the cooling phase. And we will see that often, that either during the heating phase itself, the connections will rupture or deform or break. Or if they don't do that during the heating phase, at least during the cooling phase, this will happen. And that happens over and over again. Several buildings I can show you the examples of. Okay, and that is something that is not addressed in the international codes yet. Why? What is the problem with the with the international codes, including the Indian code, that we cannot address this issue of thermal movement? I showed you some examples of how to design a column. Similar examples are there for how to design the beam also. So you calculate the load on the beam. The load is service load, right? So that is the gravity load. So you calculate the gravity load on the beam, and you calculate the moment capacity at elevated temperature.
Maybe, sir, failure of a column is more catastrophic, so they are focusing more on that instead of a beam. Failure of a beam is a localized.
No. I have shown you example of failure of a column, but there are provisions for failure of the beam also.
Okay.
For the gravity load, you calculate the moment capacity of the beam, just like you design the beam at ambient temperature. There are equations in the Indian code as well as the American code, or whatever the temperature versus yield strength and temperature versus elastic modulus curves are available. They can be applied to the beam equations that are given in the Indian code, and you can calculate the residual beam strength. But even that does not suffice, or that's not sufficient to address this issue. I think the answer is pretty obvious. I'm surprised that you guys are not.
Beams are more.
No, it's got nothing to do between the beams and the columns. This particular type of a failure, it happens in beams only, but the problem is fundamental. Yeah, Prithvi?
In the design, we only consider the heating phase. We never consider the cooling phase.
Okay, so but at least the heating failure, you're getting to the right answer, but at least, see, I said that this beam, when it wants to expand, it will be pressing against the column. So even in that phase, if it's a bolted connection, there is a chance that that bolt will fail. And that has happened in a few cases. So at least that should have been addressed. But in none of the codes, international codes, can address this issue, even if you design as per the best Indian international code, as of today. Okay, so the scientific approach that I discussed with you, even with that approach, it does not allow you to, or it does not give a recommendation how to incorporate the thermal expansion effects. Okay, so if you look at that equation, there is no provision for thermal expansion effect. It's only talking about the reduction in yield stress and reduction in the elastic modulus. So the forces that are generated because of thermal expansion, that are not addressed at all in the in any of the international codes. And by any of the international codes, I mean the ones that are prevalent. I mean, any international code is a very generic definition. So yeah, like European code, American code, Indian code, Australian code, New Zealand code, British code, at least these I can vouch. They don't have a provision to address this issue. And this is a very, very commonly occurring theme in many buildings, right? Then another issue could be that under fire, your beam starts to lose the bending moment capacity. It forms a hinge. Okay, so some of the Indian code and some of the other international codes now can address that hinge formation because of moment. So you have a gravity load acting, you have fire. Because of that, the moment capacity decreases and you form a hinge. And then after the hinge formation, sometimes you can even resist the load through a catenary action. Okay, so you understand what a catenary action is?
Yes, sir. Like in cables.
Yeah, like in cable. So what happens is that even though the beam may have lost the moment capacity, right, but still there is a reinforcement, or not the reinforcement, there is still a steel, right? So it loses the moment capacity, but still it has not completely lost its tension capacity. Some portion has yielded, but the beam has bigger cross section. And then maybe there is a concrete slab also, which was designed to be in compression, but now it is in tension, so it can resist some tension. And all that, it can actually start to behave like a cable or like a rope. Okay, and for that rope to act effectively, you may need some strong connections here. And if you have, for some reason, that kind of strong connection, which is uncommon, but still it's not a completely impossibility. So in some buildings, you may have that kind of a connection at the ends. And if you have that, then it can actually start to behave like a cable. And for that cable action to happen, yeah, your columns, wherever you are anchoring these beams with, those columns should not bend inward, right? So if the columns start to bend because they are not designed for this, then this catenary action will not take place. So these are the secondary effects. For the World Trade Center 1 and 2, this is what they say was actually happening. The beams were losing their moment capacity and they were turning into a cable. And all that gravity load had to be supported. So in a beam, the vertical load comes from in this manner, right? So if it was a beam, you apply the loads on a beam vertically downward, and the reaction forces come this way. Correct? That's how a beam behaves. there is no horizontal component of that force if the load is not horizontal. Correct? But in a cable, this is what happens, what you see here. The forces have a huge horizontal component. And if you have a column that is supporting this beam, then that column should have been able to resist this lateral force demand. Right? So the column should be strong enough or stiff enough in the lateral direction to resist that kind of a force demand, which can sometimes be very huge. And what they say about the World Trade Center 1 and 2 is that there were very long span beams which were connecting the internal core to the external columns. And the external columns were not really very heavy duty because that was a tubular kind of a structure where the outer structure is kind of a tube, which is made of thin, small, lightweight columns, large number of them at close intervals. Okay, and they were individually not strong enough, and when these beams pull onto them, the columns were not able to resist that. Okay, so the first building I will talk about in this context, where the beam failure or the connection failure takes place because of the thermal expansion, is Alexis Nihon Plaza in Montreal. I don't have a video for that one. They didn't have a video footage. At least I could not find a free video footage. In 1986 in Canada, as per the provisions of the fire safety in those days, it was adequately protected. So there was enough fire protection applied to beams and columns. Okay. And it had a steel beam with composite slab. So steel beams by themselves are very uncommon, especially in buildings. In industrial structures, they may still be there, but in buildings, you would always have steel beams with a concrete slab on top. Okay. So that's what the system they had used. And 10th floor fire ignited at 5 p.m. and the fire responders came soon enough. Several firefighters were trying to fight the fire. You can see some flames coming out of these windows, but the fire could not be controlled. And so there were major fire losses above the 10th floor. And on the 12th floor, so you can always see that the fire starts on a different floor, but then by the time the building collapses or some collapse happens, the fire had moved to a much higher floor, and that's where the collapse is triggered. So on the 12th floor, after about 2 to 3 hours of fire, the collapse took place. Okay, and then after that also the building continued to burn for several hours, but they were able to control the fire after eventually. So when they investigated the failure, they found that there was this kind of a connections. There are several such connections in this typical building. You have a column, you have a girder, and the girder is connected to the column through this kind of a shear-only connection. So this kind of a connection is known as shear-only connection, right? Simple connection. In the Indian code also, we have an annexure which gives you different types of acceptable connection designs, and there are simple connections or shear-only connections or pin connections. So these can be idealized as pin connections. Why can we not call them as rigid connections?
Flanges are not connected.
No welding is it.
Yeah.
No,
So flanges are not connected to the column. Until you connect the flanges rigidly to the column, you cannot call it a fixed connection or rigid connection. It can only be called a pin connection or a shear-only connection. So only the web is connected with an angle. The web of the beam was bolted to the angle, and the angle was welded to the column. Okay, so this is weld and this is bolted connection. And what they found was that these welds were failing. Okay, so this is a common theme you will see in several such buildings where these welds start to fail first. Okay, so weld between the column to the girder connection had failed. And obviously, as I had explained to you, because this beam would initially try to pull or push against the column. So this weld failure usually does not take place during the push, because when the push is taking place, you have large bearing area, right, wherein the angle can bear against the column. So during the pushing phase, you would not expect this weld to fail. You can expect these bolts to fail during the pushing phase. But if the bolts are strong enough, it can sustain. Or if there is this clearance between the beam and the column is not there, if the beam is almost touching the column, with some expansion, the beam goes and starts to resist or starts to bear against the column, then the force transfer will take place very easily through this bearing, and there won't be any issue. Okay, so during the push phase, usually the chances of failure are low, and especially this kind of a weld failure won't take place. But that can take place when the pulling comes. So when the fire dies out and the beam starts to pull, there can be this pulling force for two reasons. One, either the fire has died out and the beam is pulling back because it is contracting now, or otherwise the beam has lost its moment capacity and it has gone into catenary action mode. Then it would want to pull on the connection. So either of the two things happened. Probably it was the cooling phase of the fire that happened, and that led to this failure of this weld. And as soon as this weld fails, the beam has no other support, so beam will start to collapse. So there was a partial collapse on some floors, but it did not continue to the rest of the structure. So it was not a kind of a progressive collapse that you may sometimes see. It was a partial local collapse. This was a very interesting building, One Meridian Plaza in Philadelphia, USA. The previous one was from Canada. The design practices in the US and Canada are very similar. So this was a 38-story steel building. There was something very interesting about this building. All the frames in this building were designed as moment resisting frames. Okay. So when I say all the frames were designed as moment resisting frames, what does that mean for beam column connections? How were all the beam column connections designed?
Rigid connection.
Rigidly connected, sir.
Absolutely correct. So typically what happens in a building is that you either have braced frames. Okay. So then let's say you have a building, maybe I can draw a little bit. So far I have not drawn much. So you have a building plan. Maybe I have discussed this thing before also. In a braced frame system, typically I can pick one brace here or one frame here. These are the column locations. With this circle, I'm marking the column locations. Okay, and there might be columns inside also. I'm not marking all of them. Let's too many, 4 only. Okay, so this is the building plan. Okay, so you have got 4 into 4, 16 columns. But for a braced frame system, typically we will do a braced frame here. We will do a braced frame here. So these frames, when I'm looking from the front, typically it will look like this. Okay, so this don't have braces. Any of the internal columns, internal connection beams, these frames will also. So these are all frames, right? So this is one bay, this is another bay, this is another bay, and these individually you can call it a frame from here to here. Okay, so none of these frames are braced. Actually, only this here, this here, this here, and this here. This you can brace, and that is usually good enough. So that is a typical bracing configuration, braced frame configuration. Sometimes we don't like braces. Why don't we like braces? Because wherever we provide the brace, we cannot provide a window, or it becomes difficult to provide a window. Okay, and the connections are also a bit challenging. So often we don't like, architects don't like braces until they unless they want to incorporate there in their scheme. Usually, so like if I want to buy a house and I have a window and there is a big steel kind of a I section going right across the window, I would want to pay less for that house, or I would not want to buy that house or office or whatever, right? So immediately the property prices go down as soon as they put a brace somewhere, and that brace is ugly and sitting across the window, right? So you can see a lot of in block B, when we were being allocated, all of you won't enjoy this thing. Let me show you a picture of block B first, and you will enjoy. This class is more of a storytelling. Huh? Yeah, we had about academic building. Yes, this one. Yeah, this is a better picture. Yeah. Can you see this photo now? Can you see this photo?
Yes, sir.
Yes, sir.
Yeah. So in this one, you can see this is not a braced frame building. This is a very peculiar type of a building. I'll not even get started. Anyway, you can see this kind of a diagonal members on alternate floors, right? So if I call this one as ground floor, then this is first floor, third floor, and fifth floor have these diagonal members, right? So in a braced building, braced frame building, you will have these diagonal members, and you can see these vertical windows that are there. So because of these braces, the second and fourth floors were more popular among faculty members when we were being allocated these rooms. The second floor and the fourth floor were occupied first, most of them. Then the first, third, and fifth were picked. And the obvious reason is because your windows were being blocked, partially though, but they were being blocked by these bracing members, right? So that immediately brings down the property value. So architects don't like to do it. You can't blame them. So coming back to that discussion. So if you have braced frame, there's some issue, but they are still very commonly used because they are very efficient way of resisting lateral loads. If there is any lateral load acting on this building, by providing very tiny, small cross sections here, we can manage to get a large amount of lateral stiffness. The other option could be to go with the frames, the moment resisting frame option. Okay, there are other options also. I will not talk about them in this class. So in a moment resisting frame system, what we do is for a moment resisting frame, the rest of the column beam connections or rest of the frames here, we can assume them to be pin connected. So this is the beam, this is the column. Here we will provide a pin connection, meaning that if I look at that detail closely, this is a column, this is the beam, and I'll connect only the web of the beam to the column with the similar connection that you just saw in that Canadian building. Okay. However, at certain locations, so for example, here I was making this frame as a stiff frame or laterally placed frame. In a moment resisting frame, I will make them rigid. Okay. These connections will be column, beam, and then I will not only connect this part, but also I will connect the flanges. Okay, and they have to be rigidly connected. So there are detailing requirements for rigid connection that I have to satisfy. Fine. So if I do that, then I can call this a moment resisting frame. And usually when you go for a moment resisting frame, a single frame will not be sufficient. A single frame for a braced frame may be sufficient often for a decently sized building, but a moment resisting frame, typically it won't be sufficient, or it will be very uneconomical. You have to go for very, very heavy beams there. So alternatively, we often go for a distributed moment resisting frame, wherein you use the entire frame as a moment resisting frame. Okay, so the entire frame here, all the connections here are rigid. All of these connections can be rigid, but these ones can be pinned. Fine. So in this particular building, instead of going for this kind of a system where only the exterior frames were rigid and the internal ones were all pinned or only gravity load resisting, they had put all the connections, every single connection, every single beam to column connection in this building was a rigid connection. Okay, so that's why this was a moment resisting frame throughout. Okay, and then it was fire protected also. The building caught fire on the 22nd story, and it burned for 19 hours, the entire building. It does not mean that the fire was staying at one place for 19 hours. The fire was continuously moving from one floor to another. One floor burns for 3 hours, fire moves. After maybe 1 hour or 2 hours, the fire moves to the next floor, and so on. So some of the floors had sprinklers. Wherever they had sprinklers, they were able to stop the fire, and the fire eventually, because of that, died out. But until the fire reached that, and everything under those floors, wherever there was no sprinkler system, the building burned for a very long time and consumed everything that was to be consumed. Okay, they were trying to douse the fire. The building was unoccupied, or they were able to evacuate the entire building. So there were no residents who could lose life because of this thing, but there was a major risk of building collapsing. Okay, and if this was downtown Philadelphia, so if the building were to collapse, this would have caused a huge damage to the city. So they were trying to extinguish fire, but the fire was so severe that they lost several firefighters in that struggle. And eventually they decided that let's let the building burn out and let it consume whatever fuel it wants to consume. We will not be able to control the fire. They were kind of bracing themselves against the possibility of building collapsing, but the building collapse never happened. When the fire died out, they went into the building. They saw that some of the floors had deformed so much. So after this kind of a deformation, it obviously means that the beams had lost their moment capacity, and they had gone into a catenary action. Okay, but the rigid connections that they had provided at the ends of the beams probably held them together. Okay. They did some forensic investigation. They took samples of concrete and other steel and other materials, and they took it to the lab and tried to see what was the maximum temperature on those elements. And some investigation suggested that that temperature was definitely more than 530 or 580, whatever critical temperatures they consider for beams. So beyond that temperature, typically beams lose their moment capacity. The temperature was beyond that, but still the building did not collapse. Okay. This is a picture of World Trade Center 7. So you have all seen the examples of the videos of World Trade Center building 1 and 2 collapsing, right? Now, World Trade Center building 1 and 2, these were the tallest buildings, not at the time in the world, but they had been tallest buildings for some time. They were hit by these two fighter, not the fighter jets, the passenger planes, commercial jets, and in that terrorist attack, and the two buildings had collapsed. Both buildings had collapsed, but those are not the only two buildings collapsed in that vicinity on that day. This was a building in the neighborhood, which is known as World Trade Center 7. This building was also the headquarters of FBI, Federal Bureau of Investigation. Okay, this was a very prominent building. In fact, the other two, the main two buildings, Tower 1 and Tower 2, had more commercial value. But if you talk about Government of America's assets, then this building was more important, World Trade Center 7. So this is a picture taken from the top, from here. Okay, and the other two towers, the primary ones, they had a airplane impact, right? So there was a reason, or there was a doubt whether those buildings collapsed purely from fire, or they collapsed also predominantly because of the impact force. Because of the impact force, there was a big fire, but also several columns were knocked out because of that impact. So that could have led to the collapse of that building. This building had no such reasons to cause confusion. This building was not hit by any plane. It had some falling debris from the big two towers. When the two towers collapsed, some of the debris fell into these buildings. That lit fire in this building. But that was there was no structural damage because of that debris. Only the fire was lit. And then this building collapsed completely. Here is a video of that collapse. So you can see that in that corner, some components have started going down. And then you can see here something is happening. Some glasses started breaking. Okay, and then the entire building implodes. Again, I'm playing the same video. It started here. Here you can see something happening on the surface. And then the building implodes. Okay. Again, for this building, when they did the investigation, this is the plan of the building. These are the internal columns. These are the exterior columns. You can see again, the exterior columns are very closely spaced. You can see these beams, how closely spaced these beams are. That is a sign of this tubular kind of a structure. So this column is there to support one beam each. So this also had a relatively tubular kind of a structure, but it was not, these beams were typical I-section beams. Unlike World Trade Center 1 and 2, you can, there are a lot of investigation done on World Trade Center 1 and 2 also. You can read that on your own. I'm not covering that topic, that particular building here, because there is a lot of material available on the internet. And also those buildings had an airplane impact also. So there was a combined effect. This particular building had pure fire accident. So if you look at the plans of this building, I don't have, no. So if you look at the members that they had used in this building, these beams were all I-section beams, unlike World Trade Center 1 and 2. World Trade Center 1 and 2 had more of this trusses kind of a system for beams. So in spite of that, some of the longest beams were used here. So the collapse, when you saw it, that was this end of the column, this end of the building that was collapsing initially. And it was identified that column number 79 had failed first. And what they figured was that this beam that was connecting 44 to 79, you can see column number 44 and 79, right? You can see it, right?
Yes, sir.
Yeah.
Yes,
so this particular beam, it was being pushed and pulled because of the same effect, thermal expansion effect. It was pushing against the column and pulling against the column over several stories. And either during the pushing process, or most likely during the pulling process, this connection between the beam and the column was failing. And when it failed for first story or the second story, it did not collapse. But then this kept happening as the fire moved up and up in the building. This kept happening over several stories. And then eventually this column did not have any support from lateral direction. It had lost the support, because these beams are not only getting the support from the column. See, the beams at each floor, they get the support from the column because otherwise they will fall down. But also they provide a support to the column. How? Because the column cannot move laterally at that location. Similarly, at the lower floor, at this floor as well as at this floor, the column cannot move laterally. And that's why you take this length between the floors as the effective length of the column. Correct? So they fix the L value for the column. Otherwise, and if this connection is gone, and that connection is gone over several stories, then the effective L for the column will be very large. and that's what happened to this column, and that this column collapsed. Of course, these findings are based on some simulations, some kind of analysis, some photographic evidences, etc. You have to take them with a pinch of salt. Nobody exactly can figure out what happened inside that building on that day, but this is what the best analysis can suggest. Okay. Now, moving forward, there is another type of effect that fire has that is also related with thermal expansion, but it is thermal expansion of columns. Okay. So let's say I have a frame like so, and which is supported on a column. And if this frame has beams which are very, very stiff, okay, and they are rigidly connected to the column. In fact, sometimes you may have a situation where the beam is continuous over the column. Okay, so it's a continuous member over the column. Again, I'll show you an example of this one since I have this picture opened already. You can see this building. You can see this building, B block, IIT Hyderabad. The top beam here, you can see that the column is going and connecting to the top beam also, right? But I don't think this connection is really a very rigid connection, because eventually this top frame is hanging from this column. So that's not that kind of a system. But alternatively, there may also be a possibility where the column terminates here and then it is simply resting on this beam. So this frame, you can see how heavy it is, right? What is the cross-section size here? You can see the bulkiness of this column, of these beams. So imagine that you have something like that. Sometimes this kind of a frame is called a transfer frame. Its main purpose is to transfer the loads between the columns. Okay, so you have this kind of a beam and you have a column, and because of the fire, the temperatures are not very high yet. The column has not failed under that temperature, but it has only expanded. But if it wants to expand, what it has to do? It has to bend that beam, because at the other ends you have other columns on that beam which are not expanding. So they don't want, so at these ends, the beam does not want to move up. So over here and over here, the beam does not want to move up. It wants to move up only here. So the beam has to undergo bending. As a result, what will happen is that this column will undergo additional compressive demand, and the beam will undergo a moment demand, right? So there will be additional compressive force on the column, which is more than the original gravity load. Right, so there will be additional, in addition to the original gravity load, there will be additional compressive force on the column. Likewise, on these beams, there will be a moment demand at the ends, right? So this particular example is of that kind. So this is Broadgate Phase 8 building in the UK, and 14-story building. Here, lattice truss. This was the typical column frame system. So you can see this was a small I section used here. This is a small I section. You can see small I section here also. So in this direction, the span length was less, and they had used not a very deep, rather shallow I section. And in this direction, the spans were very long. So they had used this kind of a lattice truss. This is the similar kind of a system they had used in the World Trade Center building 1 and 2 also, between the columns. So in this direction, this lattice truss was connecting the individual columns, also even the beams. So you can see there is another column here, there is one column here, and in between the two columns you have this beam, and between the space between this beam and the subsequent beam in the other direction, in this direction, you can see this kind of a lattice truss that is going. Similarly, it is going here also. These lattice trusses have a very high efficiency as far as bending moment capacity is concerned, and they behaved all right, they performed fine. Fire protection was also not there to full extent. I think there was some issue with the fire protection also. So the structural temperature rose very rapidly. Then what happened is that these columns, when they were able to douse the fire, the building did not collapse, thankfully. When they doused the fire, they went inside the building. They saw that several of the columns had deformed like this. Okay, so this clearly shows like what kind of deformation it is. What would you call it?
Local
buckling, sir.
Local buckling primarily, yes. So, but these columns must have been designed to behave or to not undergo local buckling, right? Because these are standard I sections or whatever, white flange sections. So they should not have undergone local buckling. So probably it was yielding followed by local buckling, correct? Because the way codes work is that they don't allow local buckling to happen, because when you pick your section, if you go for any hot rolled section, the T by D ratios or B by T ratios will always be small enough so that you never have local buckling before yielding. So probably yielding happened before that, and then the local buckling happened. So what you see is local buckling, because yielding you cannot see. Okay, so, but yielding must have happened. Fine. So when they investigated, they figured that at least in these regions where this kind of a failure had taken place, the column had not really exceeded very high temperature levels, which would have caused the column to yield if the loads were at the service load level or at the load level which were present at that time. So probably the column load was, or column compression force in the column was much higher than what the building was applying on it directly through gravity forces. So it was not the gravity forces that are acting on the column. There is some other force acting on the column. And the reason for that was that they had a transfer frame, very rigid transfer frame. Rigid transfer frame at the top story. So similar to the academic block B, there was a heavy transfer frame. Now academic block B is not really a transfer frame. To some extent, it is somewhat, it has a slightly different purpose. But in this particular building, it was a transfer frame which was connecting all the columns together with a very, very heavy duty, very bulky frame. And what it does is basically, it does not allow uneven movement of the columns. So if one column wants to move up or expand, then this transfer frame will push it down. Okay, because it is connected to all other columns also, and those columns don't want to expand along with it. So because of that, probably this column failed. But even after the failure of this column, failure of a gravity load bearing column is a big deal. If a column that is carrying gravity loads fails, that is the death nail for you. Like, that is the final word. I mean, the building should collapse, but the building did not collapse even after gravity load bearing column's failure. The reason for that is that even after the column failed, then it wanted to go down, right? So initially, let's say this is the transfer frame at the top. There are several columns connecting here. This is the column that is in fire. Let's say it is expanding. It wants to expand, but the frame does not let it expand. So the column buckles locally. Okay, so it fails locally. Now, when it has failed, it cannot carry its own gravity loads. So it wants to keep going down. But for that to go down, it has to bring the frame along with it, right? And the frame does not want to go down with that column because it is connected to other columns. It will transfer the load to the subsequent columns. So that's why the building got saved. So essentially, what it means is that higher level of redundancy in this building, as well as if you see the One Meridian Plaza building. This one. So in this building, all the frames were designed as moment resisting frames. That provided it an additional level of redundancy. Similar thing happened in this building also. There was an additional level of redundancy because you were having a redistribution of forces through that transfer frame. So these things are some of the obvious things. Of course, higher level of redundancy helps with the progressive collapse particularly, and that led to a good performance of such structures. Okay. Okay, so this is pretty much it. This is the end of this lecture on fire safety, structural fire safety. I think we have some 25 minutes. We can close it today early. If you have any questions, I can answer them.
Sir, in the project topic, I have some.
Yeah.
Sir, sir, in the question you asked us to consider the constant wind load, sir.